Good morning, everybody. Here we are starting our final learning target for section 2 or unit 2. It is about rational functions. It's going to be awesome. I love this one. And there's a variety of problems here. Or there's a variety of things that we need to know for these problems. So first of all, let's just get a decent idea of where rational functions where they come from, because they look pretty weird. Like they look like this. They have this going on. They have some sort of vertical asymptote going on. Well, it didn't come out of nowhere. It is very, very logical where it came from. So let's try to just understand where it comes from. Let's start with y equals x minus 4. We all know what that looks like. That's just a line. But what about y equals 1 divided by x minus 4? So suddenly this is a rational function. And let me show you. I created this spreadsheet here. So you have x values going down this column, and then these are y values. This is the x value minus 4. So in other words, it's the line. If x is 0, the y is negative 4, because 0 minus 4 is negative 4. And there's your ordered pair. If x is 1, 1 minus 4 is negative 3. So there's another ordered pair. So all these ordered pairs are on this line. So if I were to graph all these ordered pairs, it would look exactly like a line. Well, what about 1 divided by x minus 4? Well, when x is 0, that is 1 divided by 0 minus 4. But what really a good way to think about it is it's just 1 divided by the line, because it's 1 divided by x minus 4, and this column is all the x minus 4s. So 1 divided by negative 4 is negative 0.25. So 0, comma, negative 0.25 is on this graph, the rational graph. Another one, when y is negative 3, well, 1 divided by negative 3 is negative 0.3 repeating. So there's another ordered pair. And 1 divided by the y value of negative 2 is negative a half. So here's another ordered pair, 2 comma negative a half. Getting the x's from here, and the y's are just 1 divided by these y values. And on and on and on and on and on. So all these ordered pairs. Now notice, this is important. When x is 4, back on the line, when x is 4, the result is 0. So the number 4 is a 0 of this line. So it's an x-intercept. But 1 divided by this y value, you can't do 1 divided by 0. So division cannot divide by 0. So this function over here, this rational function, does not understand what 4 is. 4 is just not in the domain of this function. And what I did was I graphed all those ordered pairs to see what they would look like. Well, there's the line, y equals x minus 4. Again, notice that when x is 4, the result is 0. And all those ordered pairs I put right here. And this is kind of like the beginnings of our first rational function that we're kind of exploring. If you take this line has many, many y values. And if you take 1 divided by each y value, you're going to get these red ordered pairs. So for example, this is the y value of 6, 2, 4, 6. And if you take 1 divided by 6, you get 1/6. So the ordered pair would be existing right about there. And it has a vertical asymptote at x equals 4, so I can graph that. And here is our function. Here's our rational function, shooting right through all those ordered pairs. And it'll never cross this vertical asymptote. It may look like it does, but it does not, because this rational function cannot receive x equals 4. 4 is not in the domain. So it'll never, ever, ever cross or touch x equals 4. So that is a vertical asymptote. Vertical asymptotes are never crossed. Horizontal asymptotes may be crossed. In this case, it isn't, but that's not a rule. There's a horizontal asymptote of y equals 0 right here. All right, so now that we have a rudimentary idea of where these things come from, we're going to really analyze the cuss word out of them. So if we could graph rational functions by hand, then we are going to be feeling really good about ourselves. Rational functions, talking about a division of two polynomials. So just one polynomial divided by another. That's all we're doing in this chapter. And to graph these, we have a lot of clues where you can find a horizontal asymptote. Some have them, some don't. A y-intercept will help us. That's always the result when x equals 0. We're going to factor p and q, so we're going to factor the numerator and the denominator. That's going to help us find asymptotes and holes. And we're going to find x-intercepts. The x-intercepts are the x values that make this whole thing equal 0. But that's just really finding out what makes p of x equals 0. What makes the numerator 0? In the example, just some reminders about these asymptotes. Learning target 2 was about points of discontinuity. Remember, any point of discontinuity, anything, is an x value that makes you divide by 0. I'm not talking about piecewise functions. Piecewise functions are kind of like their own animal. You can have jumps in piecewise functions, but we're not talking about piecewise functions here. Just one single rational function. And any point of discontinuity is an x value that would make you divide by 0. So I need to find the x's that make q 0, the bottom 0. And so to do that, I would factor both top and bottom, factor both p of x and q and x. And once I factor, if anything cancels out, then it's a whole, remember? And if it doesn't cancel out, then it's a vertical asymptote. I hope you remember that from Learning Target 2. It was also on our quiz a couple weeks ago. Horizontal asymptotes are something we learned in Algebra 2, and you are forgiven if you forgot, because that's just human nature right there. But let me remind you, if the degrees of p and q are the same, if they're the same degree, then there's a horizontal asymptote, and it's just the division of the two leading coefficients, the leading coefficient of p divided by the leading coefficient of q. If the degree of p of the top one is less than the degree of q, then the horizontal asymptote is just simply y equals 0. And if you're really listening hard, there's another case that I haven't really talked about. What if the degree of p is actually greater than q? Then there is no horizontal asymptote. Okay, so for a quick example, here's a rational function, x squared minus x minus 6 divided by this. You're going to factor pretty much every time you see this. So just factor, factor, factor. The top factors into this. The bottom, I got a GCF of 3, difference of squares, and here I am. So at this point, I know there are 2 points of discontinuity, 2 and negative 2. Well, the negative 2 portion cancels out. That would indicate that there's a hole at x equals negative 2. Now, the other point of discontinuity, positive 2, did not cancel out. So that tells me there's a vertical asymptote at x equals 2. And then way back in the beginning, notice the 2 degrees are the same. It's second degree and a second degree. So that means there's a horizontal asymptote of y equals 1/3. I just divide the 2 leading coefficients, 1 divided by 3. This is the problem that we investigated first, and it's all worked out for us. We're given this, and the horizontal asymptote is y equals 0, because the degree of the top is 0, there's no x's. The degree of the bottom is 1, so if the degree of the bottom is ever bigger, it's just y equals 0. And I graph a little horizontal asymptote, y equals 0. A y-intercept, plug in 0 for x. If I plug in 0 for x, I get negative 1/4. So that's an ordered pair, and I plot that right there. That helps me understand where the graph is. Any holes? No, because nothing cancels out. No factors cancel out between top and bottom. Is there a vertical asymptote? Yes, x equals 4. Makes you divide by 0, and that factor did not cancel out. So I get to graph that. X equals 4, vertical asymptote right here. And my graph will never cross a vertical asymptote, never. X-intercepts, that's what makes this whole thing 0. And since it's a rational function, I just need to concern myself, how could the top ever be 0? Well, the top will never be 0, because the top is always the number 1. It's not like it says 1x or 1 plus x. there's no x value that would make the top 0. So there is no x-intercept. And you draw your, so this, you don't have a lot to go on. You have a vertical asymptote, you have a horizontal asymptote, you have a y-intercept right here. So this y-intercept indicates that you could draw this graph. Notice how your graph is approaching both asymptotes. The asymptotes are kind of acting as guidelines to help you graph it. And the other portion is up here. If you type in a number like the number 5 or 6 into x, you would get a positive number. So that tells me that I'm positive up here. And again, the asymptotes are helping me guide. It's just approaching both of those asymptotes. Here's another one. This one's really unusual. First of all, notice the degrees are the same, x squared, x squared. So that means the horizontal asymptote occurs by the division of the two leading coefficients. 3 divided by 1 is 3. So y equals 3 is a horizontal asymptote right there. The y-intercept, let x equals 0. If x equals 0, these two go away, and you're just left with 4 divided by 2, which is 2. So there's your horizontal asymptote right there. Holes, 3x squared plus 4. There is no x value that makes this 0. Well, actually, no real x value. There are imaginary x values, but we're not talking about imaginaries. This is a real plane, so there's not going to be a physical hole here. These are all real numbers. So there's no hole. And what about vertical asymptotes? Well, you could try really hard to factor this, but it is completely prime. There's nothing. This does not factor. And again, if you were to set this equal to 0, you would get two imaginary numbers, which tells you that it's not factorable. So I really don't have a lot to go on. This is a weird example. There's no vertical asymptotes. You have one, what's it called, y-intercept. You've got a horizontal asymptote. Again, the asymptotes really help because it guides the graph. I know that my graph has to go through this point. I also know that when x gets really small, or when x gets really big, the function will be approaching this asymptote. So that's how I can guess that it looks something like this. All right, let's do something. Let's do this. Oh, never mind that. Delete. So we're going to graph this as best as we can. First thing, there's a lot of starting points here, but it doesn't really matter where you start. Horizontal asymptote is listed first. Well, look at these degrees. They're the same. So that means there is a horizontal asymptote, and it is the division of the leading coefficients. So the horizontal asymptote is y equals 1, and I get to graph that. So I go in my notes, if I were you, and try to graph as best as I can a horizontal asymptote. Boom, right there. Y-intercept. I love y-intercepts. If you let x equals 0, what do you get? Well, if you let x equals 0, this goes away, this goes away, this goes away. So you're just left with 6 over negative 9. Well, 6 over negative 9, doesn't that simplify to negative 2/3, I believe? So negative 2/3 is the the y-intercept. And that's something I could plot. So I'm going to plot it. We'll choose blue. 0, negative 2/3. So now I know two clues about my function, about my graph here, which is a function. It's going to be approaching this horizontal line, but it's also going to be going through this ordered pair. Those two things must happen. Any holes or vertical asymptotes? Well, to discover these, I must factor. So I factor. It factors into this, x plus 3 times x plus 2 divided by this difference of squares. Did I factor that correctly? Oh, yes, I did. Now, what does this tell me? First of all, it tells me there are 2 points of discontinuity, negative 3 and positive 3. The negative 3 part, the x plus 3 factors, they cancel out. So that tells me that there's a hole at x equals negative 3. Once I factor that out, once I cancel that out, I'm left with this kind of reduced version, and you would plug in negative 3, that's where the hole occurs, to find out the x value, or the y value, which is 1/6. So that is the hole. Negative 3, comma 1/6. Now, how do you graph that? We'll graph that last. I'll show you how we do that. Vertical asymptotes? Well, yes, 3. X equals 3 is a vertical asymptote because x equals 3 makes you divide by 0, and it didn't cancel out. So there is a vertical asymptote at x equals 3. And I get to graph again. I can graph a vertical asymptote. We're still going with red. Good. X equals 3. Okay, any x-intercepts? X-intercepts are the x values that make the whole function equal 0. Now, there are two numbers that make the top equal 0, -3 and -2. But -3 is already out because -3 is a whole. So I'm just left with -2. X equals -2 is the x-intercept. And if you're thinking, oh, now he's going to plug in -2 to see what it equals. No, because I'm talking about x-intercepts. If -2 is an x-intercept, then the result is 0 for sure. -2, 0 is a ordered pair, which I get to plot, and that's right there. All right, now I think I'm ready to graph. So first of all, I have two big guiding lines here. So my graph, obviously in the bottom left, I'm going to graph through these two ordered pairs, and it's going to be bending towards these asymptotes. The other side, now the other side, is it going to be in the upper right or is it going to be in the lower right? Well, it's usually symmetrical through this cross, but that's not a rule. It's just often that happens. You could do a quick check right here, like plug in an x value that's bigger than 3. So you could do 4, 5, 6. You could do 100. Doesn't matter. Let's just do 100. So 100 squared plus 5 times 100 plus 6. If you divide that by 100 squared minus 9, can you see that you end up with I don't know what you get, but you get a positive number for sure. You get a positive number. The top is much bigger than the bottom. Oh, I'm sorry. That's not the reason why. The top is a positive number. 100 squared plus 500 plus 6. I don't know what that is, but I know it's positive for sure. It's a positive. And 100 squared minus 9, I don't know what that is either, but I know it's positive. So a positive divided by a positive is another positive. So I'm graphing up here. And now 2 more steps, guys. I'm going to graph this guy, doing my best. I'm going through these order pairs and then letting those asymptotes guide me, do the best that I can. And then I know that it's in the upper right over here, so I let the asymptotes guide me. That's the first step. I said there were 2 steps. What could the second step possibly be? Well, remember that whole at -3 1/6? So you're going to take your little eraser and go at -3. Doesn't it look like the y value is 1/6? Erase. And then take your pencil again and draw a hole. There you go. And that's full credit. You're going to get a 4 on this. 7 more. Just 1 more. Last one. And then no homework this weekend. Enjoy yourselves. Last one, but you have to do this one. All right, graph this puppy. Well, horizontal asymptote, look at the degrees. 2nd degree versus a 1st degree. Hold on a second. They're not the same. And the top is bigger than the bottom. So that means there is no horizontal asymptote. No horizontal, which means I can't graph it. There is an asymptote. You could divide these two things and the result would be the asymptote, but that's not part of our curriculum. Y-intercept. Let x equals 0. If x equals 0, what do you get, guys? What do you get? -2. So 0, -2 is the y-intercept, and I get to graph that. I can graph y-intercepts. Let's do purple. Another ELF reference. Oh, I think it was a different class. Purpley dress. Okay. Holes and vertical asymptotes. Well, I have to factor. Clearly, x cannot equal -2. So there's a point of discontinuity when x equals -2. But the top factors into x minus 2, x plus 2. The denominator is already factored. It's prime. The denominator is just x plus 2. So, oh boy. So what do I discover? That since that canceled out, that is a hole. Hole at x equals -2. So there is no vertical asymptote either. There's a hole at -2, however. And what's the y value? Well, what's left over after I cancel out that factor is x minus 2. That's the thing that's left over. So if I plug in -2 into there, I get -4. So that tells me that the specific ordered pair of the hole is -2 comma -4. 2 comma -4. And there is no vertical asymptote because there's only one thing that made me divide by 0, and it canceled out. So that's the hole. X-intercept. Is there anything that makes the numerator 0? Yeah, there are two things, +2 and -2. Remember, -2 was the hole, so that doesn't matter anymore. +2 is the x-intercept, 2 comma 0. I'm a little bit behind in graphing these things. So 2 comma 0 is the, what's it called? The x, whoop, the x-intercept. There's a hole at -2, -4. And check out these 3 dots. Remember, there's no horizontal asymptote, so there's no horizontal line guiding my graph. There's no vertical asymptote, so there's no vertical line guiding my graph. In fact, after I factored and canceled out common factors, I was left with x minus 2. And you know what that is? That's a line. Y equals x minus 2 is a line. So there is a line with a y-intercept of -2 and a slope of +1. And check it out, y-intercept right here and a slope of 1. And it goes all the way through, but I don't want to cut through this hole right there. Come on now. So there it is. A line, a line, a line. This whole thing is a line, but with a hole right there at -2, comma -4. Hope that was clear, and have a great weekend. I'll see you on Monday.